Okay, let me proceed here. So in order to write the node equation for that node, I'm going to sum the currents exiting the node, and so let me do that. So the current going up is simply V naught minus Vs divided by RL. That's the current going up, and then the current going down is simply ID. Okay, and that is 0. I can multiply out by, notice that I have not replaced the actual equation for the current yet. I'll do that in a moment. So I'm going to I'm going to multiply out by RL, and so multiply out by RL, I get ID RL, and then I'm going to move Vs to the right hand side, leaving V naught on the left hand side. So I'll leave V naught on the left hand side, I move Vs to the right hand side, and move ID RL also to the right hand side. Okay, so there is my V naught in terms of ID. So now let me go ahead and substitute for ID. So I'm going to substitute this expression for ID into the expression here, and that will give me V naught equals Vs minus k divided by 2 V in minus 1 whole squared times RL, and this is for V in greater than or equal to 1 volt. Now what happens when V in less than 1 volt? So what's the value of V naught when V in is less than 1 volt? Well, when V in is less than 1 volt, ID is 0. Okay, so when ID is 0, then V naught is simply equal to Vs. Okay, this is for Vn less than 1 volt. Okay, so let me mark this down into a box because I am going to be using it, and just so we don't lose sight of it, let me go ahead and put this into a nice little box and put a little star around it. So we've done the quick analysis of this dependent source circuit, and I've obtained a V naught versus V in relation that I set out to do. Okay, so when I said solve it, I was looking to have you do a V naught versus VI relation for me. So really, there's not much else to this. So just keep this picture in mind, and let's go ahead and plug some numbers into this equation to see what it really looks like. So on the right-hand side here, I've just summarized what you've seen so far. This is the expression that I had marked with a star. This is not a great-looking star, but pretend it is a star. And so this was a circuit I showed you earlier, and V naught equals Vs minus the current times RL for Vi greater than 1 volt, and V naught equals Vs for Vi less than 1 volt. Let's plug in some numbers. So for example, let me say that let me choose Vs equals 10 volts. Let me pick K to be 2 milliamps per volt squared, and let me pick RL equals 5 kilo ohms. So let me go and solve this for these values of the various devices. So for the case, I have two cases here. So there's two cases, 1 and 2. So for case 1, for Vi greater than or equal to 1 volt, here is what I get. I get V naught equals, so Vs here is 10 volts. So let me write that down as, let me just go write this down again for convenience. Vs minus K by 2. Vi, notice that Vi equals Vn, so I can just use Vi here, minus 1 the whole squared RL. And so Vs is 10 minus, so K is 10 to the minus 3 milliamps, that's 10 to the minus 3 amps, divided by 2. And then I have Vi minus 1 whole squared, and RL is 5 times 10 to the 3 ohms. So I can simplify this whole thing a little further. And so what do I get? So in this case, I'm going to get the following expression. When I take I've forgotten to substitute for the 2 for k, so it's a little bit of a blunder here. There we go. I put a 2 there. Okay, that works. So let me simplify this out a little bit. So 2 and 2 cancel out. 10 cubed and 10 raised to minus 3 cancel out. So I'm left with 10 minus 5 Vi minus 1 whole squared, and this is for Vi greater than 1 volt. And then for Vi less than 1 volt, what do I get? I get V naught from 2 from here, I get V naught equals Vs, where Vs equals 10 volts. So I can plot these expressions. So there's V naught here for Vi less than greater than 1 volt, greater than equal to 1 volt, and then V naught equals 10 volts for Vi less than 1 volt. Let me just go and plot this for you. It's not too hard to plot. So this is my Vi axis, and this is my VO, and this is 0. There are a couple of interesting points on this curve. Certainly one of them is the 1 volt point. So let's see what we have. So we start with Vi at 0. So when Vi is 0, in fact, when Vi is less than 1 volt, V naught is 10 volts. So let me write down 10 volts here. And so what this says is that Vi, until Vi is 1 volt, V naught is going to be 10 volts. What happens next? So when Vi is greater than 1 volt, then this equation takes hold. Notice that if I substitute Vi to be 1 here, I get 10 volts as expected. And now, as Vi increases, as Vi increases, I subtract the square of Vi times 5 from 10. So, so starting from 10, I'm going to subtract a value, and that value is going to be related to the square of Vi, okay, times 5. Okay, so this is going to be increasing as the square of Vi, and so therefore, as I subtract that from 10, I'm going to get a curve that is steeply falling and looks like this. Okay, so this curve is given by 10 minus 5 Vi minus 1 whole squared. So that's a plot of this curve for the dependent source circuit that I've just shown you. Okay, so this is the VO versus VI plot that we had set out to discover.